Hello, this is the 8th video in a little mini series that I'm calling Basic Limit Theorems. And in the previous video we looked at the law of large numbers, the strong law of large numbers and the weak law of large numbers. And we proved the weak law of large numbers in two different ways in that video. And then I said there's going to be a third way to prove it, but it's a little bit longer and we're going to use a dedicated video for it. And here what we're going to do is we're going to prove the weak law of large numbers without the assumption of finite variance. Okay, so that's what let's set out to do. So the weak law of large numbers says if we have a sequence of variables xj from 1 to n, their IID with finite mean, then the sample mean converges in probability to mu. Okay, so let's prove that. So for any delta greater than 0, let's define two random variables. Okay, yj, and it's going to be like an indicator function, but instead of 1, we're going to have it equals x when x is less the absolute value of x is less than delta n, and 0 if it's greater. And z is going to be the opposite. It's going to be 0 when xj is less than delta over n, and it's going to be xj when we're beyond that. And this is for all, j equal 1 to n. So then we can, then xj is yj plus zj from 1 to n. And we will restrict to the continuous case and the f be a PDF for the x's. First of all, we want to show that this variance is finite. So let's look at the variance. So the variance of yj, really, since they're IID, let's just look at the first one, the variance of y1. And that is expected value of y1 squared minus the mean squared. So since this is a positive number, if we remove it, then this number is bigger than this number over here. And this number, since it's the way the function was defined, so you put values in here times its probability. So it's either xj with probability that x is less than or equal to yn, or 0 times that probability. But 0 times anything goes away. So this is these two values are the same. The expected value of y1 squared times this. Well, the expected value is, it's the integral of what's in here times the density. So this is it. But if we restrict it to this, 0 outside this region, really we're just saying we're integrating from delta n to minus delta n, or minus delta n to delta n of this. Well, if we break this x into x times x, and for one of the x's, let's put in the maximum value that we achieve. Okay, then we're going to have to call this other x absolute value of x. And that's what we do. So we put in the biggest possible value that this can take, and then and the other is absolute value of x. So this is true. Now, and then if we go ahead and extend this back to infinity, and because these are both positive, this piece is a little bit bigger than that piece now. But the way this is by definition expected value of x1, which in our assumption that this was finite. And of course, for a given n, this is finite and delta is finite. So the variance is finite. Okay, that's going to play a part here. Next, let's look at the mean of yj. So it's expected value of y1, which is this expected value, and by definition that equals this. Okay, so we don't really know much about that yet. So let's look at this. Let's look at this inner piece here, okay, and see what happens. So if we take the absolute value of this inner piece, it's this. then that's less than or equal to the, this absolute value of this times absolute value of this times absolute value of this. And then, but then this is 0 or 1. So if we just think of it as 1, it even got bigger, but the absolute value of 1 is 1. So this is less than or equal to this. And since this is always positive, we don't need absolute values around it. So this piece is dominated by this. And, okay, so, but if we just look at this piece by itself, as n goes to infinity, it equals x times f of x, right? This region kind of just big, and then it's really just the expected value, or the x times f of x, okay? And this piece here, by definition, is finite, okay? That was part of the assumption. And so by the dominated convergence theorem, then therefore this integral, which is expected value, if we take the limit of this, we can pass it inside because of the dominated convergence theorem. And this piece goes to that, which is mu. So the expected value of xj goes to mu. Now let's keep building little pieces here that we're going to put all together. So here, let's look at the mean of yj minus expected value of yj. And let's look at the probability of the absolute value of that being greater than epsilon. Here, so if we take this n to the other side, that's what this is. And then we need n of these, which is like saying the expected value of the sum of these yj's. So these two probabilities are the same. Now, Markov's inequality says that if the variance of this sum, divided by n squared epsilon squared, this is greater than that. And but since they're IID, so it's really n times the variance of one of them. And then we just showed that the variance of this is finite and equal to n times, or delta n times expected value. It's less than that. So now we start cancellation and we get this. All right, so this probability is less than or equal to this probability. So it's finite, okay? Next, let's look at this probability, the sum of, or the mean of our yj's minus mu. So it's very close to this, but we're going to stick in mu here. And we want it to be greater than 2 epsilon. So when we go to this probability, all we do is we add expected value of yj and subtract expected value of yj. So we're adding 0, so it doesn't change this probability. Now, since we have the absolute value of this quantity, this is going to be less than if we just look at the pieces here, the absolute value of the pieces. So that's what we do here. Now this next step is not obvious. And the way the way that I like to go from this step to this step, which you can't see yet, is if we look at a Cartesian coordinate system and call this absolute value of x, say. So x should be on the abscissa. And this is the absolute value of y, and call that the ordinate axis. And then plot this region for that being greater than 2 epsilon. It ends up being like a little diamond region, and then everything outside that is shaded. Okay, so now this is less than or equal to, if we just take the probability of each and divide it, and divide this by 2, greater than epsilon, plus probably this greater than epsilon. So again, think of this as absolute value of x, absolute value of y, and on this same Cartesian coordinate system. So in the diamond that this created and everything else was shaded, this one actually cuts into the diamond, and then everything else is shaded. So this region is bigger than this. So this probability is greater than that. Well, we just showed that expected value of yj converges to mu. So the probability that's greater than some small number is 0. So this goes away. And then we showed up here that this is less than or equal to this number. Okay, so now let's keep going. By assumption, we said that this value was finite. Okay, but let's break this up into pieces. The region where absolute value of x is greater than delta n and absolute value of x less than or equal to delta n. So both of these pieces are finite. And then if you let n go to infinity, this piece goes to 0, and this piece goes to, just the absolute value of the integral of absolute value of x dx, or f of x. Okay, so now here, since this piece goes to 0, for any, we can find an n big enough that this is really, really small, less than some number, some small number. But of course, as n goes to infinity, it does go to 0. But if we, if we stop at some n, and we can find that n, that this is less than some really, really small number. Okay, so now let's look at the probability that zj is not 0. So that means that the absolute value of zj is greater than delta n. Okay, but that really means xj, because the way that zj was defined. So the xj is greater than n. And then this probability is really an integral, so we're integrating the density over this region here. Okay. Well, again, we're going to use the trick that, if you divide delta n over here, then that number is greater than 1. So if we put that number, which we know is greater than 1, times the density, this just got a little bit bigger. Okay. Well, then we can factor out the delta n, and then we're left with this. Well, we just showed on the previous page that this, as n goes to infinity, this goes to 0, or at least something very, very small. So let's let this at least be smaller than, say, delta squared. And we're just picking an arbitrary small number. So n, at some point, this gets less than delta squared. Okay, so we have 1 over delta n, and then this gets smaller than delta squared. Okay, and then of course one of the deltas cancel, and we're left with delta over n. And of course this is as n goes to infinity. So now, instead of looking at one of those, let's look at the sum. Right, so it's the same. But since they're IID, we can look at, it's going to be less than n times one of them. But this here is less than delta over n, so the n's cancel, and it's less than delta. Okay. So next, and this is the finality of our proof here. This we want to show this probability goes to 0. If we can show that, then the mean converges in probability to mu. And we're going to let it be. You show that this greater than some really small number, say 4 epsilon. Okay. Well, here we replace xj by yj and zj, right? Because these are equivalent to xj. Now, what we do is we take this minus mu in with this, and then we take the absolute value of each of those, and so that's going to be greater than this quantity here, the absolute value of this plus absolute value of this, greater than 4 epsilon. So now we're going to use the same trick that we used before, where we divide that by 2 and take the individual probabilities. So this is greater than that. And we have to, again, it's 2 epsilon instead of 4 epsilon. Well, this piece we're going to carry down, and this piece, the absolute value of this, if we take the n to the other side, that's the absolute value of this sum greater than some small number. So if we take that small number and just say it's 0, then this probability just got bigger. So we're saying it's not 0. Well, here we showed that this is less than delta, and we showed that this is less than this number here. Okay. So now if we replace delta, say, by another small number, say epsilon cubed, then for every epsilon greater than 0 and n goes to infinity, then this probability is less than this. Okay, so where we replaced it epsilon cubed, in here. We get epsilon times this. So now this is true for every epsilon, no matter how small. So if we let epsilon go to 0, then this side goes to 0. This is a finite number. So you keep letting epsilon go to 0 and 0 and 0, then it equals 0. So this probability in the limit is less than or equal to 0, right? So that means it has to be 0. And so that's the definition of convergence and probability, is that this probability that this is bigger than any small number goes to 0. Well, we're done. All right, well, that's all I have for today. I hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. The next video, we're going to look at what's called the continuous mapping theorem, which is another powerful tool that we use. So I'll talk with you then. Thanks. Bye.